Good morning, all, and welcome to our last lecture of CHY 113 for the fall 2020 semester. We're almost there. It's been a long and challenging semester for all of us, but we can see the light at the end of the tunnel now, and we just need to push through to the end. And so let's go ahead and start today by looking at some examples of some of the gas law calculations that we looked at last time. And actually, these examples that I've chosen are directly from some of the practice problems, so you may have seen these already. But in case you haven't, or just for some extra practice, go ahead and work on these problems here. These are all various gas law questions. And so go ahead and pause the video now, work through these problems, and see what you can come up with. And here we see the answers. And so note these down. If you got them all right, great. You're on the right track. You're understanding how to use the gas law equations and when to use which one. And you're understanding some of the algebra, which can be a bit challenging for some of you sometimes. And so just to talk about these a little bit, what we have to do here, obviously, the first thing that we have to do for each problem is figure out what relationship we're talking about and figure out what the appropriate gas law is that we need to use. And so we can see in the first one that we're dealing with pressure and volume. And so that tells us that so that's the only information we're given is pressure and volume information. And so we can assume that all other parameters that aren't discussed are going to remain the same. Therefore, that would tell us this is a Boyle's law situation. Let's just go through that same analysis with all of these, and then we'll look at the solutions and how I set these up so you can look at that as well. In our second problem, we are given volume and temperature information. And again, nothing else, and so we assume that all other factors stay the same. And so that tells us this is a Charles's law situation. Now, remember, the way we differentiate between, if we're going to use something like Charles's or Boyle's law versus the ideal gas law, is that in problems like Boyle's or Charles, we're given two set points. We're given two points of time, kind of, in information. We're given a first set of conditions and a second set of conditions. And we're asked to look at how one of those factors changes with changing conditions. Versus an ideal gas law situation, we're given one set of conditions and we need to find the missing parameter. And that's what our last problem is. In our last problem, we don't have two different sets of conditions, we just have one. And we see that we have an unknown quantity of gas, an unknown amount. We're given a pressure, we're given a volume, and we're given a temperature. So that tells us that this third one is an ideal gas law situation. And so let's just look at how I set each of these up. Oop, you don't need to see that. Okay, and so here's the first one. So here's our Boyle's law situation for problem one. And so I'm going to go through these fairly quick. I'm actually not going to spend time on them. I'm just going to scroll through them. But this is where you could, if you did get this incorrect, pause the video here. Sorry, that's the third one. There we go. If you did get that incorrect, pause the video here, look at my setup, see what I have done, and see if you can find out where you went wrong. So there's our Boyle's law for the first sample problem. Here's our Charles's law set up for the second problem. Those of you who did get this one wrong, I'm guessing, or one place to take a peek anyway, is look at your algebra going from our general form of Charles's law over to then solving for T2. Talked about this a little bit in the video where we talked about gas laws, where you do have to be careful with this algebra sometimes. It's a very common mistake if you're solving for something that is down in the denominator. And so make sure that you are comfortable with the algebra going from here to here. And lastly, our ideal gas law situation. And so those are three sample gas law problems. And so what we're going to do with the rest, or with our final lecture, is we're going to spend a lot of time talking about what we call intermolecular forces. And what looking at intermolecular forces will allow us to do is to start to investigate some questions such as, at room temperature, why is water a liquid and not a gas? Even though, for instance, something like methane Methane with its atomic mass of roughly 16 versus water with its atomic mass of roughly 18, nearly identical in size. Yet methane, CH4, is absolutely a gas at room temperature, but water is not. And so likewise, why does water boil at such a high temperature? We really have to heat it up quite strongly in comparison to similarly sized molecules. We'll look at things like why ice floats on water. And actually, we're not going to answer all of these, but all of these sorts of questions, snowflakes having 6 sides, I2 is a solid at room temperature versus Cl2, which is a gas. All of these types of questions and all of these factors of some of these physical properties can be attributed to these intermolecular forces that we're going to talk about. Intermolecular forces play a huge role in determining the physical properties of various substances. And so the forces that actually hold liquids and solids together are these intermolecular forces. Intermolecular forces are the attractions and repulsions between separate molecules. And so they're the forces that would hold H2O molecules to each other. It is very important to differentiate here between intermolecular forces and actual chemical bonds. We'll see a diagram of that in just a minute and really look at and see what that difference is. But be sure to note that when we're talking about intermolecular forces, what we're really talking about are attractions between separate molecules. We are not talking about actual chemical bonding. The intermolecular force that a substance might exhibit is a function of what the charge might be on the molecule, the polarity on a molecule. Remember, we talked about polarity as it relates to molecular shape and electronegativity. And it may be a function of the molar mass, the strength of these intermolecular forces. And we'll talk about all of these things. Intermolecular forces influence chemistry in lots and lots of different ways. As I mentioned, they're directly related to properties such as melting point and boiling point, and looking at some of these physical properties. They're very important in determining solubility of gases, liquids, and solids into various elements. And they're also really crucial in looking at structures of some molecules such as DNA and proteins. When we look at the actual double helix structure of DNA, the reason why DNA is held in that structure is because of some of the intermolecular forces that are involved. The reason that, if you remember, sort of back to your basic biology, when you look at the base pairs in between that backbone, adenine pairing up with guanine, for instance, then, did I get that right? I hope I got that right. Thinking back to my biology, it's been a while. But those base pairs that are in between that backbone, those base pairs are held together by intermolecular forces. And so these intermolecular forces play a huge role in lots of different properties. We're going to focus in a lot of our discussion in looking at states of matter and how intermolecular forces determine if something is a solid, liquid, or a gas at room temperature. It turns out, and we're going to look in some more detail at these, but if in looking at if something is a solid, liquid, or a gas, it's a balance between the kinetic energy, the motion of the particles, how much energy the particles have, versus the intermolecular forces, which are the attractions holding the molecules together. And so let's just take a look at this illustration here. We've seen this before. We've looked at this this simulation before in looking at the molecular motion of particles in their various phases. And so here we have water in its solid phase. You know, remember we talked about there is still some motion there, but ultimately that motion, that kinetic energy of the particles is not enough to overcome the attractive forces that are holding them together. The intermolecular forces that are holding the individual water molecules to each other is more than the energy that the molecules have. Therefore, they stay together in their solid form. If we heat things up a little bit, though, so we heat things up and get into the liquid phase, now we can see that the molecules have much more energy. And that energy is just enough to start to overcome these forces. And so what happens in the liquid phase, and you can see this as you look through some of these molecules here, as you just sort of watch them interact, is that a molecule might have just enough energy to overcome the forces holding it to another one, kind of shifts its position, and then reforms those forces again with another molecule. But the molecules are starting to have enough energy now that they can start to overcome those intermolecular forces that hold them together. We heat things up even more to the gas phase. Now we're at a point where the molecules have so much energy, so much kinetic energy in the molecules, that they completely overcome any of the intermolecular forces that hold them together. And so that's really what determines if something is going to be a solid, a liquid, or a gas. Do the molecules have enough energy to overcome the intermolecular forces that are holding the molecules together? That's ultimately what is going to make a difference here. And so let's just talk about what intermolecular forces really are. We have intramolecular forces versus intermolecular forces. An intermolecular force, these are the bonds that we've talked about before. And so covalent bonds, ionic bonds, and so forth, those are intramolecular forces. And so those would lead to molecular stability. Is the molecule itself stable? Ionic versus covalent. As opposed to intermolecular forces, these are now the forces between individual molecules, the forces holding entire molecules to each other. And they'll lead to things like some of what we consider the bulk properties, things like freezing point, boiling point, and so on. So let's take a look at a diagram and see what that really means. And so here we have a couple of HCl molecules. We have a covalent bond that holds the H to the Cl. And so the hydrogen is bonded to the chlorine in this case, a very polar covalent bond. That's a very, very strong bond holding the two of these together, holding the hydrogen to the chlorine. And we can see, in fact, the strength of that bond, 432 kilojoules per mole. That means for every mole of these molecules that we have, it's going to take 432 kilojoules to break that bond, to separate them from each other. As opposed to the force that holds two HCl molecules to each other. That's the intermolecular force, the intermolecular attraction that holds these two molecules next to each other. That's only a 20 to 30 kilojoule per mole interaction. So you can see much, much, much smaller force that holds these together to each other versus what holds the whole compound together. And so that's a covalent bond, an intramolecular bond versus an intermolecular force. Another way that I think about it is sometimes is think about the terminology used in sports. Intramurals. And so if we think about intramurals at USM, intramural sports, those are sports being played amongst students within the same university. And so you're going to get together, maybe you're going to form a team with some of your dorm mates against some other dorm mates. But you're all within USM. Similarly here, an intramolecular force is within the same exact molecule. Intramural sports within the same school. Interscholastic sports, now we're starting to play against St. Joe's and some other universities. Intermolecular forces, we're looking at the interactions between the two different molecules. And that's one way that you can try to keep the two terms distinct in your mind, if that helps. And so intermolecular forces, like we've mentioned, are directly related to properties such as melting point and boiling point, and the energy that's required to convert solids to liquids or liquids into gases. And they're also very important in determining the solubilities of gases and solubilities of various substances in general. And like I had mentioned, some of the structures of some important molecules. There are four primary types of intermolecular forces we're going to talk about, starting with the weakest, with London dispersion forces. London dispersion forces are fairly weak forces that occur actually in all molecules, and we'll talk about these. The strength of an intermolecular force depends on the size of the molecule and something that we call the polarizability of it. We have dipole-dipole forces starting to get a little bit stronger. Dipole-dipole forces will occur between two different polar molecules. We have hydrogen bonding, which is actually a special consideration or a special type. Oops, sorry, let me pause you for just a minute so I can take care of what I'm doing here off screen. Okay, and we're back. And so a hydrogen bond is a special type of a dipole-dipole interaction. I'll mention this again when we talk about hydrogen bonding in a few minutes, but it is important to note that even though we call it a hydrogen bond, it's not a true bond. It's still an intermolecular interaction. And then finally, we'll look at ion dipole forces, which typically occur between ions and polar solvents. And so let's start by looking at London dispersion forces. And so London dispersion forces occur in molecules that do not have a permanent dipole. And so whether that is because there are no dipole bond, no polar bonds at all, or if it's because there are polar bonds that are all symmetric and cancel each other out. Remember, we talked about that when we looked at molecular structure and polarity. But whatever the reason is, if we're talking about a molecule that is non-polar, then we're looking at the only intermolecular force being present would be London dispersion forces. These forces are present in all molecules, even polar molecules. However, they are the only force present in non-polar molecules. And so let's actually keep our discussion to non-polar molecules for now for London dispersion forces. And so what can happen is just if we think of something like CH4, we think of something like methane. Remember, all the electrons that are involved are in constant motion. Electrons are never static. They're always moving around the molecule. As they do so, due to this random movement, we can envision a point in which there are more electrons on one side of the molecule. That ends up producing a very, very, very slight charge separation. Not nearly to the point of the charge separation that we talked about with polarity. But we can start to envision that, okay, right in this snapshot in time, there are more electrons over here. So we start to build up a little bit of negative charge over here and a little bit of positive charge over here. And that's just the one, if we just take a quick snapshot of the molecule, we might see this. In the next instant, it's just going to disappear because the electrons are still all moving around. And so it's going to disappear and things will be evenly distributed again. But then we might take a snapshot in the very next instant in time, and this separation forms again somewhere else. When this happens, when this little bit of separation happens, this is a very, very temporary and weak dipole, which would continue to just form and go away in the absence of other molecules. So if we just have a lone little CH4, a lone little methane molecule floating around, this is going to continue to happen, and that'll be it. This will just continue to occur, and that's the end of the story. However, if this methane is next to another one, then when this happens, when this little bit of charge separation occurs, it can impact the molecule next to it. And so here we have three different methane molecules. In the middle one, we get that little bit of charge separation at that one instant in time. If there's another molecule near it, then that molecule is going to be affected by this temporary dipole in this one. And so in this case, we have a negative buildup on this side of the middle molecule. And so that's going to repel some of the electrons in this molecule. Likewise, the small buildup of positive charge here is going to attract the electrons in this CH4. And so then that'll start to line things up a little bit. Now we start to end up with a situation that's a little bit more permanent, because this attraction is now going to exist between these molecules, and then boom, there we have it. And so this is a London dispersion force. London dispersion forces result from a temporary weak dipole occurring in one molecule, but then that temporary weak dipole in one molecule affects the other molecules around it and creates a more permanent situation. Very, very weak attraction, but it does exist and it helps hold molecules together. And so some of the things that can be factors in forming dipoles. So again, like we talked about, we have a couple of nonpolar atoms or molecules. We get this momentary attraction, and then we induce a dipole in another molecule. And so the formation of a dipole in one molecule creates that dipole in another molecule. A very, very weak dipole, but still a dipole. For that reason, London dispersion forces are sometimes called induced dipole forces. And they're going to be present in all atoms, molecules, or ions. And they happen due to this asymmetrical distribution in the electron cloud that just randomly occurs. London forces will have different strengths depending on certain factors. The higher molecular mass a compound has, the stronger the intermolecular force will be. And so if we have something like, let's just look at a couple examples here. And so two different hydrocarbons. Let's say we have C4H10, we have butane versus maybe C6H14. So we have butane here, hexane here. Don't worry about these names. Those of you that go into organic chemistry down the line, we'll see where these names are coming from. But we have two different hydrocarbons. Now, these are both made up of just carbon and hydrogen. So we know that both of these compounds are nonpolar because there's not enough of an electronegativity difference between carbon and hydrogen to form a polar bond. So these are both completely nonpolar molecules. All right, sorry for that little glitch in the video. Hopefully things are still working out okay. And so back to here. So like I said, these are both nonpolar molecules. C4H10 is smaller, has a lower molecular mass than C6H14. That's going to mean that in C6H14, there are more electrons that can be moving around and creating these temporary dipoles. That's going to lead to a stronger force that would hold hexane together. That ends up being reflected in the boiling points of these compounds. The boiling point of butane is roughly -1 degrees C. The boiling point of hexane is roughly 68.7 degrees C. And so that occurs because hexane's larger, more electrons that can contribute to the London dispersion forces. And so there are more forces that would hold hexane together, which makes it harder to separate the molecules, which means we have to give it more energy for these phase changes to occur. And so that results in a higher boiling point. And so remember, we talked about that's really what's going on when we think about phase changes. It's this interplay between the forces that hold the compounds to each other versus the energy that the compounds have. And so if you have more forces holding the compounds to each other, you're going to need more energy to separate them. And we see that with a higher boiling point necessary for hexane compared to butane. And so that's just comparing two molecules that only exhibit London dispersion forces. London dispersion forces are also affected by something called polarizability. The larger the molecule, the more polarizable it is. The easier it is for the electrons to shift around and form these temporary weak dipoles. Also, just the larger a molecule is, the more surface area is available for the London dispersion forces to act upon. And so if we have, for instance, and this goes a little bit beyond some of the things that we would talk about in this course, but if we have maybe, switch over, here we go. So this compound here, which would have the chemical formula of what, C5, right? 1, 2, 3, 4, 5, yeah. 1, 2, 3, 4. So C5H12 versus this compound here, which also has the chemical formula C5H12. Exact same chemical formulas, but the way that these are combined are very, very different from each other. We have the top compound, which is going to look like kind of a ball. And so when those are held together, we're going to have these ball-like surfaces that are interacting with each other. Versus the shape of the molecule on bottom is more like a flat sheet. They're going to fit together more like this. And so the one on bottom has more surface area for those London forces to act on. Therefore, it would take more energy to separate them. And so this one on bottom is going to have a higher boiling point than this one. Even though it's the same exact chemical formula, the surface area on this one is so much more than the surface area on this one. And so that's another thing that has to be kept in mind when we're looking at these forces. We talked about this. We talked about some polarizability. Sometimes we call it the squishiness of a compound. And so remember that it's in nonpolar molecules, the only force that will be present is a London dispersion force. And so that would be in situations where we have molecular geometries that are linear, with both atoms being the same, or the outer atom is the same if it's what we would call triatomic. And so, for instance, if we have something like H2, that's going to be a linear molecule, all symmetric, both atoms the same, obviously a nonpolar molecule. Or if we have a triatomic linear, something like carbon dioxide, now we have a linear molecule, but our outer atoms are the same. And so nonpolar. And then in some of these other shapes, triganoplanar, tetrahedral, trigonobipyramidal, octahedral, essentially what you're looking for or one of the things you can look for to determine polarity is if you have any of these shapes here, linear, triganoplanar, tetrahedral, blah, 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 blah. If you have any of these shapes and they're completely symmetrical around that central atom, it's going to be a nonpolar molecule. Any deviation in that symmetry, however, is going to lead to a possible polar molecule depending on electronegativity differences. And so something like HCN, now we have a deviation in symmetry. We don't have the same two atoms on the outside, and so we end up with a polar molecule. If we have CH4, actually, let's go with a different example. Sorry. Erase. Where's my erase? Here it is. So instead of CH4, let's go with CL4. So definitely polar bonds in there. The CCl bond is a polar bond, difference of a large difference in electronegativity, but it's completely symmetrical. And so this is going to be nonpolar. However, if we now change the symmetry in some way, maybe replace even just one of these chlorines with a hydrogen, now the polar bonds don't all cancel each other out. And this would absolutely then be a polar molecule. So this just goes back to some of the stuff that we looked at in the last unit, again, with our molecular shapes and our polarity. But now we're seeing how we're going to really start to use some of that. And so this deviation in symmetry would lead to this being a polar molecule. And so that leads us to our next type of intermolecular force called the dipole-dipole force. A dipole-dipole force will exist between molecules that have a permanent dipole. And so anything that we looked at in the last unit that has this permanent dipole, that has this permanent polarity, the intermolecular forces that will exist between those molecules are dipole-dipole forces. And so these are only going to be present in polar molecules. And so let's do a little bit of comparison here. And so if we have C3H8, for instance, has a molecular weight of about 44 grams per mole, boiling point of about 231. We're not going to worry about the mu there, the dipole moments for now. But let's compare that to this molecule here, CH3CHO. And so this molecule, let's just look at the structure of this, just so we can see it. And so we have CH3CHO. If we do out the Lewis structure for this molecule, we're going to get a molecule that looks like this. And so the same exact molecular weight, but we can see now that we have a higher boiling point. That higher boiling point is due to the fact that we have this dipole bond here. And so this is a polar molecule. This is a nonpolar molecule. And so that leads us to those different boiling points of 231 degrees C. Sorry. Just realized what I had done here. This is a polar molecule. Other molecule that we had looked at was C3H8. That should have been the one that I drew up here for comparison. So my apologies there. So these are the two that we're comparing to each other. C3H8 versus CH3CHO. There we go. That's better. And so nonpolar here. And we saw that reflected in a boiling point of about 231 degrees C versus a boiling point of 294 degrees C. Again, same exact molecular weight. They're both about 44 AMUs. But the presence of this dipole means that in this molecule here, in our CH3CHO, we have dipole-dipole interactions, which are stronger than the London dispersion forces that exist in C3H8, which is propane gas. It's just C3H8. And so that's really what we're going to be looking at when we're trying to compare some of these different physical properties, compare boiling points, compare melting points, and things like that. One of the things we looked for is in similarly sized molecules, what type of intermolecular forces exist. Dipole-dipole forces are stronger than London dispersion forces. And so in two molecules like this that are nearly the same size, the stronger dipole-dipole force leads to a higher boiling point. And then finally, we get something like CH3CN. This is going to lead us into our last type of intermolecular force. In CH3N, And I should have left a little bit more space. So I want to leave this on the same page. Sorry. I knew that I did something wrong and I drew that incorrectly for the point that I'm trying to make. Should have spent a little bit more time getting ready rather than putting on my sharp duds for you. And so CH3N is going to, or sorry, CN, that's the part that I missed. That's what threw me off. So here we go. So there's our compound. Now in this one, and sorry, this doesn't actually lead us to our next intermolecular force. I was wrong about that. But what we see here is that we have even a stronger dipole. So it's still a dipole-dipole force. We have a dipole that exists right here in our molecule. So still a dipole-dipole force, but this is a stronger dipole. And so we end up with a BP that's even higher. And we're not going to worry about that as much for this course, but I did want to just point it out that this stronger dipole that exists with CH3CN leads to an even stronger force holding the molecules together and even higher boiling points. And that's what this mu is right here. It's the strength of that dipole, which is a measure of the polarity that exists. And these are just some comparisons between non-polar molecules and polar molecules that are of roughly the same size, and we can see the similar pattern. N2 versus CO, about the same size. N2 has a boiling point of -196. CO has a boiling point of -192. Not a huge difference, but there is still a difference there due to the force that exists. And we can see similar patterns in all these molecules. Similarly sized molecules, but the polar molecules have a higher boiling point, stronger forces holding them together. Talked about this a little bit, but as the polarity increases, the boiling point would increase. And so, again, we see that here with similarly sized molecules. As the polarity increases, as that dipole moment gets bigger, we end up with larger boiling points. And then finally, our last type of true intermolecular force between molecules is hydrogen bonding. Hydrogen bonding is really just a special form of a dipole-dipole attraction. Hydrogen bonding will exist anytime you have a hydrogen that's bonded to a nitrogen, oxygen, or a fluorine. And only in those cases for our purposes here anyway. And so if you have a hydrogen attached to any of those, it is a hydrogen bond. Now, it is important to note that the hydrogen must be attached to one of those types of atoms. In the cases that we just looked at, so in the case, for instance, of propane, any of these here, any of these bonds here, not hydrogen bonding. It's a carbon attached to a hydrogen. That is not a hydrogen bond. In this example, however, this is a hydrogen bond situation. We have an oxygen attached to a hydrogen. Now we have hydrogen bonding. And so what can happen, or what, essentially hydrogen bonds are stronger than your typical dipole-dipole because hydrogen is so tiny that it allows these attractions to get even closer to each other. The reason that water has a lot of the properties that it does is because of water is such a small molecule, and the hydrogen bonding allows for really, really, really strong interactions between water molecules. It leads to things like capillary action, where water molecules or water will climb up something like some filter paper. Surface tension, when you see water spiders that are walking along on water, that's because the water molecules will, so maybe here's some surface of water right here. We can picture my fingers here being the hydrogen bonding that's happening between water molecules. The hydrogen bonds are strong enough so that when a water spider walks along the water, those forces are just going to bend a little bit, but not completely give in. And so that's the dimpling that you see are those forces sort of bending a little bit. Or when you see water bead up. So when you maybe just freshly wax your 06 Toyota Corolla, so it's looking nice and sharp, and then you go out in the rain with it, and the water beads up all over it. That beading up happens due to that surface tension, the really strong interactions that occur in hydrogen bonding keeps those water molecules together. This is why ice floats. The fact that water in its solid form floats on top of its liquid form is very rare. For most substances, it's the opposite. The solid form will actually sink. The solid form is more dense. But in the case of water, let's come back to this for just a minute. So in water, the hydrogen bonding that occurs locks all the water molecules into a fixed position, into pretty much, as you can see here, kind of a tetrahedral arrangement. And so we don't think of this as tetrahedral because it's not a single molecule, but if we sort of vision it that way, we can see each of these 4 water molecules surrounding this one are sort of lined up all tetrahedral around this central water molecule. What that does is that actually spreads out the molecules a little bit. And so as it spreads out the molecules, that means that in compared to the liquid form, so here we have the same number of molecules as the solid form here. So switch back and forth between the two so we can see it. So here's our liquid form. The forces aren't holding them together and locked in nearly as much. And so then there's our solid form. The volume actually increases in the solid form. Since the volume increases, but the mass stays the same, the density of water will decrease in the solid form as compared to the liquid form, causing ice to float. Again, very unusual property compared to most other substances. So hydrogen bonds will form when you have very small atoms with a high electronegativity difference, and there also must be lone pairs. And so they'll form when hydrogen is bonded to either nitrogen, oxygen, or fluorine. And those interactions, again, are stronger than most dipole-dipole interactions. We're not going to worry too much about the actual levels of energy involved, though. But we can see that difference here. And so when we look at, when we start to look at the temperature at which certain molecules are going to boil at, we can see hydrogen telluride, hydrogen selenide, hydrogen sulfide, and then tin hydride, germanium hydride, silicon hydride, and so forth. And what we can see is that, so since none of these have hydrogen bonding, we jack way up when we add water into the mix. And I know these graphs don't quite line up, but this really illustrates for you, especially these 3 right here, that when we change it to an atom that has capability of hydrogen bonding, the boiling points shoot way up because those hydrogen bonds are so much stronger. And so it's a result of hydrogen bonding. Talked about some of this already. I'm not going to spend a lot of time there. Actually, let me just pause you again for a second because I think I'm going to skip over a bunch of this. So I'll be right back. Okay, and we're back. And so just looking at the role that hydrogen bonding plays in larger molecular structures. And so I mentioned here, for instance, the base pairs, adenine and thymine. I knew I messed that up. But so adenine and thymine coming together, or guanine and cytosine coming together. and they're going to be held together. Those base pairs are held together in the middle of the structure. So here's our sugar phosphate backbone of DNA. And here's our base pairs holding that backbone together. And so this over here is just a zoomed in portion of the backbone here. And so those base pairs, again, are held together with this hydrogen bonding. And we can see that illustrated here. And so I forget which one is which, to be honest with you. I think looking at it, this might be, okay, here's our adenine here and our thymine here, I believe. But they're held together by this hydrogen bonding. Hydrogen bonding is crucial in DNA, because if you remember, I guess, sort of back to your basic biology of and then DNA replication and what's going on there, is that the DNA has to unzip itself in order to replicate. And so the base pairs have to separate. The hydrogen bonds that hold the base pairs together are strong enough to hold DNA together, but they're not so strong that they can't be overcome and have the molecule be unzipped. And so that is key. If there were stronger forces that held the base pairs together, they couldn't unzip in the way that they do for DNA to replicate. If those bonds were weaker than they are, those forces were weaker than they are, then DNA wouldn't hold together like it does. And so hydrogen bonding provides this very nice sweet spot that is strong enough to hold it together, but not so strong that DNA can't be unzipped in order to read it, to end up going on to make RNA and so forth. And so our last type of intermolecular force that we are going to talk about is what we call ion dipole forces. These are really the forces that are involved in something when it dissolves. And so if we have, for instance, NaCl that dissolves in water, so we get our Na ions and our Cl ions, the water molecules then orient themselves according to their dipoles accordingly around those ions. And so we can see that here. Here's our positive cation. So here's maybe our sodium ion. And the water molecules all orient themselves in such a way so that the negative of the oxygen, remember this is our water dipole here, pointing towards our oxygen, our partially negative oxygen. Those partially negative oxygens orient themselves close to the positively charged cation. Here's our negatively charged anion, our Cl minus, and now the partially positive hydrogen ends orient themselves around our negatively charged anion. This is crucial when it comes to the ability of things to dissolve. This solvating effect that we call it allows things to dissolve. The water molecules kind of create this solvation shell around the ions, which allow the ions to then dissolve in water. And here's an even better picture of it. Should have gone to this immediately. And so the cation in solution will be surrounded by the negative dipoles of the water molecules. The anion will be surrounded by the positive ends of the water molecules. And we're not going to worry about the actual enthalpies, the amount of energy involved. Sorry, we're going to skip through a lot of this now. Yeah, and so then we'll just talk a little bit about the thermodynamics of something dissolving. Believe it or not, something dissolving is a more complicated process than you might think. There's energy that's required to break the ionic bond. So again, think of NaCl. We have our Na ions and our Cl ions locked together in an ionic bond. So it's going to take energy to break that apart. Energy is then, though, released when those ions are solvated. When those ions are surrounded by molecules, that then releases energy. If more energy is required to break the bonds than is released, then dissolving is actually endothermic. And we see this with some substances. If I remember right, don't quote me, but I think that CaCl2, calcium chloride, I'm pretty sure the dissolving of that is endothermic. It will actually take energy overall because more energy is required to break it up than is actually released by the solvation. And so that will cool the things down a little bit. If more energy is released by the solvation than is required to break the bonds, then the dissolving is actually exothermic. It will release a little bit of energy. Okay, sorry, we're gonna skip through. I think that actually covers most. Yeah, that pretty much covers what I wanted to talk about when it comes to intermolecular forces. This just summarizes the intermolecular forces here. Let's start at the bottom. Our first type was London dispersion forces. London dispersion forces are the only forces that will exist in nonpolar molecules. In polar molecules, we have a dipole-dipole force. In a dipole-dipole force, dipole-dipole forces will exist in molecules that have permanent dipoles. And then hydrogen bonding was just a very specific type of dipole-dipole, and they will exist when hydrogen is attached to fluorine, nitrogen, or oxygen. Okay, I was actually just going through the rest of the slides really quickly just to see if there's anything more that I really definitely wanted to cover with intermolecular forces, and I don't think there is. I'm going to go ahead and leave it there for intermolecular forces. There is a lot more information if you wanted to look at the slides themselves, but it's not information that I am going to hold you responsible for. And so remember that on the website, you do have access to all of the slides. So there is more in this intermolecular forces presentation. I'm just not going to cover it in lecture, and it won't be on your final exam. But for those of you that are curious, go ahead and go through some of the rest of those slides and see if those, just see if that interests you. The last thing that I do want to cover, though, a little bit are phase diagrams. And so when we're looking at the phase that a substance might be in, it's not only going to be affected by the temperature, it can also be affected by the pressure. And so what can happen is if you really increase the pressure on something enough, let's see if I can visualize it here. Let's return our lid. So what we're going to do in this situation here is, again, we've got some water molecules. We're going to leave the temperature the same. I'm going to put a few more molecules into there maybe. So we're at about 2 atms of pressure now. What we're going to do, we're not going to change the temperature. What we're going to do is change our volume. I guess it is affecting the temperature in the simulation a little bit, but we're not going to worry as much about that. Let's see if I can actually get a good, cool things down a little bit here. I'm just hoping that this demonstration will do what I want it to do, but we will see. Cool things down. Okay. And so we're at a point now where, oh, sorry, this really isn't going to do what I was hoping it would show. All right, we'll just go with the graph then. And so we can visualize, though, that if we have a substance maybe that's at standard temperature and pressure, and so a substance that would normally be a liquid, something like water maybe at STP, going to be a liquid. If we don't change the temperature at all, but we compress it, compress it, compress it, and compress it, down to the point now where the pressure is going to really increase on it, what we can do at that point is actually induce it into the solid phase. We haven't changed the temperature, but we've really pressurized it. And so by really pressurizing something, that can keep it in a different phase. Think about liquid propane. Propane is going to be a gas at room temperature. But we buy canisters of it. You can buy those little 1 pound canisters or the bigger 25-pound canisters that you put on your grill. That's liquid propane inside of it, LP, liquid propane. It's at a temperature that would be high enough to keep it as a gas, but it's very pressurized. So instead of being at a gas, it's going to be at a liquid. And using something like this, using a phase diagram, now takes into account both temperature and pressure and lets us know what the phase is going to be based upon those conditions. And so this is the phase diagram, for instance, for water. And so here we go. So this tells us, for instance, that if we're at about 50 degrees C and sort of maybe standard pressure. So if we're right here, somewhere in this zone here would be about STP. Water's a liquid. If we don't change the pressure whatsoever, but we start to drop the temperature, then eventually we get to the freezing point and we cross over the freezing point line. Now water is a solid. So again, this is pretty much standard pressure right here. Pressure in your rooms right now is about right here. But now we've cooled things down enough, so it's going to be a solid. We can also, however, if we're sitting right about here, and now we don't change the temperature at all, but we instead change the pressure, now we can also go from the liquid to the solid phase. And so that starts to show us that changing just one of the variables can change for us the conditions. Also, if we take if we take about room temperature somewhere in here, and we really, really, really reduce the pressure, and we get down into this point, now we've got water vapor. We're still at room temperature, but there is so little pressure that the molecules are just going to escape, and they're going to be in the gas phase. And so the phase diagram helps us take that into account, helps us take both the interaction between both the temperature and the pressure. At what we call the triple point, all three phases will exist. So in the case of water, if we're at about 4.5 millimeters mercury, really, we're talking about really low pressure situations here. But then we're also at just above 0 degrees C, 0.01 degrees C. At that point, we're going to have water, liquid, and gas all existing simultaneously. We also have something we call, I'm just going to go through these fairly quickly. There we go. We also have something we call the critical point. So here's a phase diagram for CO2. At the critical point, above 20 degrees C and above a pressure of about 73 atm, and so really, really pressurized at this point, we get what we call a supercritical fluid. And so up above that critical point is a supercritical fluid, and that's just a specialized phase, essentially. Supercritical fluids have various uses in industry, which we won't go into here, but they're essentially a specialized phase. But I wanted to more just point out, let's go back to our bigger drawing, this is what a phase diagram is. It enables us to see what phase we're going to be in, looking at various temperatures and pressures. And so at any point completely below the curve, our substance will be in the gas phase. Up in this portion of the curve, our substance is in the solid phase. And in this portion here, our substance is in the liquid phase. This also starts to show us and this will be the last thing I promise I'll leave you with. But remember, way back in September, we talked about various phase changes, and two of those changes we talked about were sublimation and deposition, where a substance, for instance, if it sublimes, goes directly from the solid to the gas phase, skips the liquid phase entirely. Carbon dioxide does this. Let's go to our carbon dioxide phase diagram. And so carbon dioxide, if we leave a chunk of it sitting out at room temperature, it's going to go from a solid directly to a gas. And so actually we'd be moving along this phase here. We'd be at a pressure of about 1 atm, so somewhere in here, and we're going to warm it up, and then boom. And so we're going to skip the liquid phase completely, because we see that for carbon dioxide needs to be at a pressure of about 5 atm before it'll ever even become a liquid. If we're not at those pressures, carbon dioxide cannot exist in the liquid phase. And so if we're at sort of a standard atmospheric pressure, so if we just take a chunk of carbon dioxide, which has to be pressurized as we keep it, or really, really, really cold, and then we put it out in room temperature, we're just skipping over our line here, never going to the liquid phase. And so, believe it or not, what I've just managed to do is take something that we talked about in September, and now we have the tools to see why something like that happens, or the tools to at least be able to visualize it and really and think a little bit more about what's going on. Everything is connected. And so that is it. That is our last lecture for today. And so, or sorry, our last lecture for the semester. So I do want to just take a moment to thank everyone for bearing with things this semester. I know it has been a difficult and challenging semester in many, many, many respects. And as I mentioned, I think in the very first lecture, this certainly is not my preferred mode to lecture. I like to be up in front of you all, doing my thing and being live with you, putting on a show. But this, I think we've all made the most of the situation. The last thing that I will leave you with is just the knowledge that, yes, sometimes no matter how well a person might be dressed as they are presenting a lecture to you, that is quite often only from the top up, and they might very well just be wearing their stained gym shorts down underneath. And so that's it. I hope everybody has a great day. As always, get in touch with me if you have any questions and so forth. And so, as always, thanks for watching.